Hello guys, I hope everything is going well with you. I'm Ali, I'm your online course instructor for the dynamic course. Today we are going to solve a problem together. Without wasting time, let's go and see what problem we are solving today. Today's problem is related to angular momentum. Let's see what is the problem. An Earth satellite of mass 700 kg is launched into a free flight trajectory about the Earth with an initial speed of VA equals 10 km per second when the distance from the center of the Earth is 10 million meter, and we call that point A. Now the question is, if the launch angle at this position is 65 degree, determine the speed of the satellite and its shortest distance from the center of the Earth at point B. And we know that the mass of the Earth is 5.97 times 10 to the power 24. And as a hint, we have that under these conditions, the satellite is subjected only to the Earth's gravitational force, and we can calculate it based on this formula. And also we know that for part of the solution, we need to use the conservation of energy. So there is only one force acting on the satellite, and that is the gravitational force. So it means that we have forces acting toward the center of the Earth that I'm calling that O, and I have FB and FA at each location toward the center of the Earth, as I'm showing that here. So now I need to know how I can solve this problem. So first, we know that we have forces toward the center of the Earth because it's a central force that I'm calling those FA and FB at each position. And also we know that this problem is related to angular momentum and also conservation of energy. So by knowing all these information, let's see what we can do. First, I'm writing down the principle of angular momentum. It tells me that the angular impulse, or the integral from point A to B, from time A to time B of the moment about point O, or the center of the Earth that I'm choosing as my reference point, would be equal to the angular momentum about the center of the Earth at point B minus angular momentum at point A. Knowing that gravitational force is toward point O, or the center of the Earth, as we discussed before, we can conclude that MO, or basically the moment of this force about point O, will be zero, which means that the angular impulse, or the first integral on the left-hand side, will be zero. Therefore, I can simplify my equation into angular momentum at point B would be equal to angular momentum at point A. That's what I'm writing. What is the angular momentum? It is basically the moment of the linear momentum about point O for B and A, and I can write it like for point B, RB, or the position vector for B, cross product to MSVB, or the linear momentum at point B, and similar for point A. And the next question is how I can calculate the cross product. The magnitude of the position vector times the magnitude of the velocity vector times the sine of the angle between them. And from now on, I will basically write down the magnitude of r as just r, and the magnitude of v, or the velocity, as just v. And at point B, the angle between the position vector and the velocity at point B, it is 90 degree. And at point A, it is alpha A, and we know that that's 65. So by knowing all these information, now we can find the relationship between RB, or the position vector, and VB, or the velocity at point B. And also I should note that in here, since I had ms, or the mass of the satellite, in both sides of the equation, I basically cancel that out. And now I have this equation that I need to solve. I don't know what is RB and VB, but I know RA and VA. So I'm going to substitute these two magnitude here and find out the relationship between RB and VB. So by replacing these values, I will have this new equation, which tells me that RB times VB will be equal to RA, which was 10 million meter, times VB, which was 10 kilometer per second, times the sine of the angle between these two vectors, which eventually gives me 9.06 times 10 to power 10. So now I have a relationship between RB and VB, or the position vector at point B and the velocity at point B, but I still cannot solve the problem. I need another equation between RB and VB to solve it. How can I find another equation? Now I can use the conservation of energy. The conservation of energy tells me that the summation of the kinetic energy and the potential energy at point A should be equal to summation of kinetic and potential energy at point B. And we know that we define the kinetic energy as half of the mass times velocity to power 2, and the potential energy for gravitational forces would be basically like this, which is minus g times mass of the satellites times the mass of the Earth over the distance, and g is basically a constant. So I replaced all these equations, and I have this new equation here. Gives me the summation of the kinetic energy and the potential energy at point A, and the summation of the kinetic energy and potential energy at point B based on the parameters that I have. Now I need to substitute these parameters, the value of these parameters, to basically figure out another relationship between VB, or the velocity at point B, and RB, or the distance or the position vector at point B. First, I should note that in this equation, I have the mass of the satellite at each term, so I'm going to cancel that out. So I don't need to include mass of the satellite since it shows up everywhere. Now I can substitute the other values and figure out the relationship between RB and VB. Substituting all the values will give me this new equation, and I changed the colors to be easier to follow each term. So first I substitute the kinetic energy, or half of the velocity at point A to power 2, which is this term, and then I replace the potential energy at point A by these values, and in the right hand side for the position B, I have half times the velocity of the particle at point B, or the satellite at point B to power 2, and this equation for the potential energy of the satellite at point B. As you can see, now I have another relationship between RB and VB, and I only need to basically reorganize this equation to give me a better equation. Then I can combine this with the previous equation that I had to figure out what is RB and also what is VB. So simplifying the equation and keeping in mind that I had another relationship between RB and VB, which was RB times VB equals 9.06 times 10 to power 10, it will give me a new equation, which is this one for the VB, and it's a polynomial equation, and I can solve it and find the VB. And solving this polynomial will give me two values. One is 10.7 kilometer per second, which is acceptable, and minus 1.9 kilometer per second, which is not acceptable because it's negative and the velocity can be negative. So right now I have the velocity at point B, and using the equation that I had before, I can find out what is RB. And RB will be 8.5 million meter. So I hope it was a good example for you guys, and I will come back with more examples. Have a great day.